Hey everyone, so we have been talking about analyzing graphs of f and f prime using critical values and talking about intervals of increasing and decreasing, all that good stuff. So now we're going to dive a little bit deeper and start actually talking about extreme values of functions. So first thing we need to talk about is local maximum. So it could be local or relative maximum. Most of the time we refer to them as local, but you do need to know that relative can also be used. But the local maxima occur when the graph of a function has a peak or a high point. Or they can occur at a closed endpoint. So let's talk really quick what I mean about closed endpoint. So if you take a look at these two graphs, in the first graph we have a closed endpoint, there's a dot at 0, and another closed endpoint, a dot at 7. When we look at the second graph though, these have arrows going on, which means this is an open interval because this is extending all the way down towards negative infinity. All right, so closed endpoint literally means we have a closed dot to end our interval. All right, so let's take a look at these graphs and actually find these local maxima. So local max, they need to occur at peaks or high points. When we look at this graph, there's actually a local max right here at 0 because in relation to this portion of the graph here, this is a maximum. So we have a local max at x equals 0. And then as we move along our graph, we have another peak or high point here at x equals 4. And then we have our final local max at the end point, which is x equals 7. Looking at our second graph, local max, again, we're looking for peaks or high points. So I see one right here, 1, 2, 3, 4, which is at x equals negative 5. We have another peak right here at x equals 0. And a final peak right here at x equals 4. All right, so local maxes just mean find the high points, find the maximums, and don't forget to check your endpoints. Okay, then we can look at local minimums. So these occur when the function has a valley, which we can also call a low point, or at a closed endpoint. So if we look at the graphs here, local mins, we're looking for low points. Well, there's a low point right here at x equals 1, and there's another low point right here at x equals 6. Looking at our second graph, I see a low point right here, which is at 1, 2, 3, x equals negative 3. And I see another low point right here at x equals 2. And what I want to talk about really fast again is these arrows. They keep going down, which means I can't identify local mins down here because it just keeps going. All right. Now let's look at global or absolute maximum. So we normally call it absolute max. The global maxima occur when the graph achieves its highest y value over a given domain. It is really important, I want to point out though, that a function does not always have a global maximum. All right, that's a really important thing for us to consider. But let's take a look at our graphs here and see if we can find the absolute max. So we're looking for the highest y value that's achieved, and that's clearly right here at x equals 7. Then if we look for the absolute max on our second graph, again, we're looking for the highest y value that's achieved. That's right here at x equals 0. And then on the other end, we can talk about having an absolute minimum. All right, so global minima occur when the graph achieves its lowest y values. And again, it's important to note that they do not always have global minimums, just like they don't always have global maximums. So taking a look at our first graph here, we're looking for the absolute lowest y value, which would be right here at x equals 1. So we'd have an absolute min at x equals 1. And then looking at our second graph here, well, we have minimums at -3 and at +2, but we have to be careful because these arrows mean that the function keeps going. So there is actually no absolute minimum in this function. Okay? An extreme value can occur at an x value where f prime is 0 or f prime is undefined. And we've talked about that. Anytime the derivative is 0 or the derivative is undefined, we call that a critical point. We've talked about that for a few days now. So extreme values can occur at critical points, or they can occur at endpoints as long as it is a closed interval. All right, so now we're going to actually start looking at how do we find the locations of the maxima and minima, and how do we find the actual maximum and minimum values. So locations, it's important to note, that means we're looking for the x values where these happen. The minimum and maximum values are actually the y values. So you want to make sure you know the difference between those. Okay, so we have 3 options that we need to look at. So option 1 is literally called an options list. All right, so I want you to think of making a table. That's what the options list is. So we use this method if we have a function with a specific domain. Or really, if we're looking at a closed interval. We most often use this option when we're looking for absolute mins and maxes. We can use it for other things also, but normally when we're looking for the absolute mins and maxes is when we use the options list. Excuse me. So we're given this function. We're on a closed interval from 0 to 3. We want to identify the location, which is the x values, and then classify all the extrema of the function. Sorry about that. So the first thing we need to do here is, of course, take the derivative. So f prime of x is going to equal -1 minus e to the 1 minus x times -1 because of our chain rule. So f prime of x is equal to -1 plus e to the 1 minus x. Once we take the derivative, we need to actually find the critical values, right? That's what we said on the last page. Extreme values occur at the critical points. So we need to actually find those, which means setting the derivative equal to 0. And when we start to solve, we get that 1 equals e to the 1 minus x. Now, hopefully, this doesn't totally trip you up, but we do need to remember how to solve this. So in order to get rid of the e to the 1 minus x, we're going to need to take the natural log of both sides. So we're going to do the natural log of 1 equals the natural log of e to the 1 minus x. The natural log of 1 is just 0. And when we do the natural log of e to the 1 minus x, these undo each other and we're left with 1 minus x. I'm going to put a star there because if you need help talking about that in class, we can definitely talk about it, but we do need to remember our stuff from algebra. But either way, we end up getting a critical value at x equals 1. Once we find the critical values, we're literally going to make an options list. So we're going to make a table. So here, I'm going to put my x values and then my f of x values. So since I'm on a closed interval from 0 to 3, those are my endpoints. And then the critical value that I found for x equals 1 goes in there as well. Now be careful because this table that we're making goes with the actual original function All right, so we're not looking at plugging these values into our derivative. We want to plug them into the original function. So if we plug in 0, we'd have 0 minus e to the 1 minus 0. So we know that that is going to be negative e to the first, which is approximately negative 2.718. If we plug in 1, we'd have negative 1 minus e to the 1 minus 1, which is 0. E to the 0 we know is 1, so we get negative 1 minus 1, which is negative 2. And then if we plug in 3, we'd have negative 3 minus e to the negative 2, and I'm going to rewrite that as negative 3 minus 1 over e to the second power. Now we need to actually identify whether these are minimums or maximums, minima or maxima, sorry. Well, the reason that I purposely changed this to negative 3 minus 1 over e squared, I know that this is going to be a little bit less than negative 3, right? It's going to be more negative than negative 3. So it's negative 3 point something, all right? And that's going to help me figure this out even if I don't have a calculator. So I'm starting at negative 2.718 and I'm going to negative 2. That means then that between 0 and 1, so on this interval, my function is actually increasing because negative 2.7 is less than negative 2. So to get from here to here, I need to increase. Then I'm going from negative 2 to negative 3 point something, which means that my interval, or that over that interval, excuse me, my y values had to decrease. Okay? That means then that at x equals 1, I must have a maximum. Look at what we just drew right here. We went from increasing to decreasing. That means at that point, that has to be a maximum. And that's actually the highest that we go on this entire interval, which means we have a absolute max at x equals 1. All right, that means then that these endpoints at 0 and 3 are both going to be minima. We know that one is going to be an absolute min and one is going to be a local min. So when we look here, this negative 3 point whatever is going to be the lowest that we go. So that is going to be our absolute min. So that is at x equals 3, which means at 0 we have a local min. Okay, so that is option 1. Looking at option 2, this is our first derivative test. So we use this option if we have a function with an open domain, or if we have the graph of f prime of x. All right, so if f prime changes sign from positive to negative at c, then f has a local maximum value at c. So let's think about what this actually means. So f prime changes sign from positive, so that must mean that it was increasing, to negative, which means now it is decreasing at some point c. So this point right here, we're going to call c. So if we went from increasing to decreasing, then we have a maximum value. If f prime changes from a negative value, which means it's decreasing, to a positive value at c, so now we're increasing, then that value c, then at that value, we have a minimum value. All right. Then if f prime of c does not, if f prime does not change sign at c, then f does not have a maximum or a minimum value. So in other words, if we had something that looked more like this, then at this c value here that we're looking at, the values didn't change. We were increasing and then we were increasing some more. So we never changed sign. That means that the function doesn't have a minimum or a maximum value. So let's look at what this actually would look like in a problem. All right. So if we're given this function, f of x equals 2x to the 4th minus 4x squared, identify the location and classify all the extrema of the function. And we do need to justify our answers. This is going to be super important, especially as we get ready for the AP exam. So I want you to get into good habits now. Okay? So the first thing we're going to need to do is actually find the derivative. So f prime of x is going to equal 8x to the 3rd minus 8x, and we want to know where that derivative is equal to 0. So first thing I notice is I can factor out an 8x, and I'm left with x squared minus 1. And I know that that's my difference of squares, so x minus 1, x plus 1, which means I have critical values at x equals negative 1, x equals 0, and x equals 1. So what we are going to do with this is we're going to make a table for our first derivative. So similar to what we have done before. So we're going to take f prime of x and we're going to make a table. Now this one is an open interval. They didn't give us anything, which means we know that we're at negative infinity over here. And then we're going to put our critical values. So negative 1, 0, 1, and then we know that all the way at the end we have positive infinity. All right, so if we were to take something between negative infinity and negative 1, let's say negative 2, and we were going to plug it into the interval, then, or I'm sorry, into the function, and let's plug it into the factored form, right? So negative, that would give me a negative times another negative, which means overall this would be negative. And then let's say I was plugging in something like negative 1/2. I need to be between 0 and negative 1. So negative 1/2 in here would give me a negative times a positive, which means on this interval we are positive. Then if I were to plug in a positive 1/2, we would have a positive times a positive, so that would be a negative overall. And then x equals 2 would give me a positive, so this interval is positive. Now, what I like to do from here is I do like to just make myself a little note that if it's negative on this interval, it means that we're going down, and then positive means we're going up, negative is going down, and then positive is going up. It just kind of helps me to see that this is the route my arrows, my function is going, all right? So what we are looking for is the local mins and local maxes. So the first thing we're going to do is identify those values. Sorry. So let's start with our local maxes. All right, local maximum occur when the sign changes from positive to negative. So from positive to negative would be right here at x equals 0. And we do need to justify this. So we know that we have a local max at x equals 0 because f prime of x changes from positive to negative. This justification that I just wrote in words has to be on your AP exam. This table is not enough evidence on the AP exam. If all you do is write local max at x equals 0, they will not give you credit for it. This justification has to be there. Okay? Now let's find the local minimum. So we know local minima occur when we change, f prime changes from negative to positive. So we have local minima, negative to positive, so x equals -1. And then we have another one at x equals +1, because again, we changed from negative to positive. So our justification here would be because f prime of x changes from negative to positive. Okay, now I'm okay with you abbreviating, but of course on the AP exam, you need to not abbreviate, all right? Okay, last thing we need to talk about then is option 3, which is called the second derivative test, and it's actually a combination, all right? So we use this option if we have a function and we are checking whether a specific x value has a maximum or a minimum there. So I'm just going to talk through what this looks like, and we're going to do this example together in class, all right? So if we're given that the first derivative is 0 and that the function is, the second derivative, is greater than 0. So let's first talk about what this c value means. So this c is some x value. So this is the specific value that we're looking at. So if the derivative there is 0 and the second derivative is greater than 0, well, greater than 0 means that this function is concave up. All right, so that must mean then that at that c value, f has a local min at c. Okay, then if we look at the derivative is 0, the first derivative, and the second derivative is less than 0, well, that means that the function is concave down, which means we must be looking at this point right here. That must mean that f has a local max at x equals c. Okay, again, we will do this example together in class because this video is already way too long. Sorry, thank you for hanging in there, and I will see you guys in class so that I can answer questions and go over whatever we need to. Bye!